Okay, hi everybody. This is great. This is welcome to one of the very first talks at CppCon 2021. So this is the Heterogeneous Modern C++ with SYCL 2020, and with me, I have a number of guests, of speakers and panelists. So my name is Michael Wong. I'm a distinguished engineer at CodePlay. Joining me will be Nevin Liber from Argonne National Lab. He is a computing scientist there. And Gordon Brown from CodePlay, who is a principal engineer, product owner, and one API on automotive, as well as Dr. Tom Deakin from the University of Bristol. He is a senior research associate there. Okay, we all hold various different positions as well at SYCL. So today's agenda is going to be about three things. We're going to talk about SYCL, we're going to talk about one API and the ecosystem. Then we're going to deep dive into quite a few SYCL 2020 features, especially the ones that are relevant to a C++ audience. And then finally, we'll look a little bit into what SYCL futures is like. So without further ado, I'm going to jump right into it. So what is SYCL? If you don't know, I'm going to give you a little bit of description. This diagram helps you to see where SYCL sits. And in the middle is where SYCL is. It is basically a single source C++ parallel programming language that takes standard ISO C++ application code, even TensorFlow, and compiles it with a host CPU compiler and a device SYCL compiler, which generates codes for many kinds of devices. Okay. So part of the reason why we're here is to talk about something that I'm really passionate about as the chair of the SYCL working group. SYCL 2020 is here and it's ready for developers to use. SYCL 2020 is released after 3 years of intense work with significant adoption in embedded, desktop, and the HPC market. There's improved programmability, there's smaller code size, there's faster performance, and it's based on C++ 17, and it's backwards compatible with SYCL 121. It really simplifies porting of standard C++ application to SYCL. It has much closer alignment and integration with ISO C++, and now it supports multiple backend accelerations and API, and is API independent. So SYCL 2020, I think, has increased expressiveness and simplicity for modern C++ heterogeneous programming. And what's more, the features of SYCL 2020 have been implemented across multiple SYCL implementations and can be used on real hardware. So I want to point out the incredible SYCL industry momentum in recent years. Most recently, you might have seen the next platform asking, can SYCL slice into supercomputing? And that is based on the announcement of the collaboration with NERSC and Argonne Leadership Computing Facility on SYCL on the Perlmutter supercomputer. Before that is SYCL and DPC++ on Aurora. DPC++ is the Intel One API implementation of SYCL you see on the top right. Then there's the NSI Tech's Kyoto microcomputer joint work using SYCL on the RISC-V vector system. There's Tricycle for Xilinx FPGA work from University of West Scotland. You're going to see a talk later on by Renan Carriel on that work. There's also the Renaissance CodePlay collaboration using SYCL and OpenCL on their R-Car ADAS solutions. And then, of course, there's HIPSYCL. This is an implementation for AMD ROCm CUDA GPUs. And then there's the TensorFlow native support on PowerVR using optimized SYCL libraries. So what is SYCL 2020? This is the SYCL 2020 is the newest release of the SYCL specification, ratified by the working group in late 2020, published by Khronos in early 2021. It follows SYCL 121, and with the version being based directly, which used to be a version that was based directly on OpenCL versions. Now, previous release following SYCL, following OpenCL base release, and in light of the move to a more generalized backend, as well as following the C++ release-based model based on the year, the project now adopted a year-based versioning scheme. Most of these features have been implemented at least once, at least in one, though many have been in all of the compilers that we have. SYCL 2020 represents a major step forward with about over 40 additional features and improvements. And we're going to go through some of these today, especially the ones that's highlighted. Then that is unified shared memory for pointer-based programming convenience. There's parallel reductions, there's workgroup and subgroup algorithms. There's improvements to atomic operations. There's class template argument deduction and deduction guides. There is simplification of accessors, and then there's also expanded interoperability with different backends. So SYCL is all about parallel industry initiatives, and the possible future roadmap of SYCL, which we released, where we released SYCL 2020 based on C++17. And this means it enables exciting C++ features like CTAD and deduction guides that makes code less verbose. There are also a number of other great features which I'm going to highlight, or actually this team here will highlight. You will also see that we released SYCL 1.1 in 2017 and previously 1.2 in 2015. And if you were to predict that we seem to be settling down to a cadence of releasing new releases every 1.5 to 3 years, matching to the ISO C++ schedule, you're going to be correct. This is because we've adapted a bus train model of delivery. You're going to see that we have changed the naming scheme from dependent on the OpenCL version to naming by year to allow us to be based on multiple backend options in addition to OpenCL, which remains our primary backend. You also see that we're projecting, tentatively of course, that a future SYCL will be released after 2021, the exact version to be named later, and will likely be based on C++20, which is already released at the end of this year, actually last year. So the SYCL ecosystem is open, and there are multiple implementations available for developers. This means that alongside one API and DPC++, there are other conforming implementations that's going to be available. And the beauty of SYCL is that your source code should compile using any of these implementations. Recently, there's also new additions from Japan called New SYCL from University of Tohoku on the NAC vector engine. And we also have a new addition that just came in from Huawei. It is called the Baishang C++ compiler that supports the SYCL heterogeneous programming standard with C++ language extensions, allowing you to program the Kumpang and Ascent architecture. So I'm sure that we'll hear a lot more about that. So this highlights the already large and growing SYCL ecosystem, starting with the implementation on the left, including the new SYCL, the Baishang compiler, and there are many research. And of this, I want to point you, make sure you notice the Exascale computing project, and Celerity for SYCL cluster. Now, these projects allow SYCL to run on exascale and petascale supercomputer systems. There's also Khronos and Raja C++, which are performance portability programming frameworks for C++ parallel execution and memory abstraction. Now, one of our working group members, Nevin Liber, who's on, is working on delivery of SYCL on Khronos. There's also GROMACS, which is a molecular dynamics package mainly designed for simulation of protein lipids and nucleic acids from Stockholm University. That is also a spec CPU benchmark and is now being accelerated for SYCL. The Alpaca library is a header-only C++14 abstraction library for accelerated development from Helmholtz and Lawrence Berkeley. Now, TaskFlow is a general purpose parallel and heterogeneous task programming system extending for task graph parallelism for distributed and heterogeneous computing. The Atlas experiment Athena from CERN is a high energy physics experiment looking for Higgs bosons and quarks from quarks. And recently we had 2 talks in GTC 2021. I never thought I would see it, by Brandon Cook from Lawrence Berkeley and NERSC, and Peter Boyle of University of Edinburgh. The next column is about benchmarks and books. Now we have the direct programming benchmark, which is a collection of data parallel programs for evaluating one API direct environments. And we also have the SYCL bench suite, which is a versatile cross-platform benchmark suite for heterogeneous computing. And this is from University of Salerno, Heidelberg, and Innsbruck. We also have a one API SYCL book now, published by my good friend James Rinder, which you probably know about, and members of Intel's team, many of which I worked together with for decades. Now, there are also on the far right, the many libraries for linear algebra, machine learning, and parallel acceleration framework now separated into what they support, like FFT, math, random, solver, sparse matrix, tensor, and STL. And at the bottom, you'll see the working group companies attending the weekly calls 1 to 2 times a week. Now here we see how Khronos standards can be used in a typical mobile or embedded application needing vision or inferencing accelerations. So neural network training typically occurs on high-powered desktops or servers at high precision using large training data sets. And the resulting trained network is encapsulated in an NNEF ONNX file that can be imported into the target system in two ways, either ingested into an inference engine such as on OpenVX, or into a machine learning compiler to generate code that execute inferencing operations. Now, either the compile code or the inferencing engine API is linked to the application, which may also use the Sickle compiler to generate additional parallel code if the application is written in C++. Okay. We're also going all in on safety critical ethics, functional safety with AI ML safety. Sickle, like OpenCL, aims to serve the embedded automotive AI domain with safety critical in the future, just like other current United Nations Economic Commissions for Europe or UNEC WP29, Khronos API, by being part of the RISC-V, MISRA, ISO SC42, 26262, 21448, and functional safety groups. Okay, and then finally, of course, HPC is a big movement right now, and high performance computing workload basically consists of 20 years, which basically persists for 20 years, while hardware can change every 5 years, often to different vendors. And they need to serve the three pillars of science problems, like simulation, which needs an HPC language with solvers and parallel runtime, or number two, data science, which needs a high productivity language for big data. And third, which is learning, training, inference needs, and which needs a high productivity language for ML. And Sickle is particularly well adapted because it enables the ability to choose an algorithm on the far right early on using basically C++ techniques from like templates and inlining, which I think other people are going to expand on. So I want to stop here and switch to section 2 on Sickle 2020 features and have Gordon Brown come on and talk about moving with the times.
Hey, thanks, Michael. So, my name's Gordon. I'm going to be presenting this part of the talk, moving with the times, where I'm going to present firstly a hello world example with Sickle, showing how Sickle works and how some of the various concepts work in C++. For those who are perhaps new to Sickle, I'm also going to show a little bit about how Sickle has changed with Sickle 2020 to show you what's new and how we've improved it. Then after that, I'm going to move on and talk a little bit about how Sickle 2020 is moving to support additional backends, as well as OpenCL, which it has traditionally. Okay, so this is the sort of typical hello world example in Sickle 2020. As you see, it's quite small, easily fits on a slide, which is nice. So what this application does is effectively takes two input vectors and an output vector of float values, and it performs an addition, element-wise addition of each of the inputs and assigns the results to the output. But it does this in parallel on an accelerator, such as a GPU or some other device that's supported by Sickle. So I'm going to step through each part and explain how this works. So first, we include the Sickle.hpp header file. This is a single header file, includes the entire Sickle API. So this is the only header file you need to include. This has changed slightly from Sickle 1.2.1, the previous version, where this was CL/Sickle. It's a minor difference, and the previous header file is still supported, although deprecated. The main reason is that CL referred to OpenCL, and one of the big changes in Sickle 2020 is that Sickle is now not only a programming model for OpenCL, but is more a general purpose parallel and heterogeneous programming model for various different backends. So in this example, as I mentioned, we're going to take two input vectors and an output vector and do an element-wise addition of each of the two inputs and assign them to the output. So here we're going to create three vectors of float with two inputs and an output, and assign them some values. Now in Sickle, all work that is enqueued to an accelerator is done via a queue object. So queues are sort of the fundamental object for enqueuing work to a device. So here we're going to create a queue which will target a GPU device. So the first parameter in constructing the queue is we provide what's called a device selector. Here we use one of the built-in device selectors called GPU selector. Effectively, what a device selector does is provides a heuristic for choosing devices. So when you provide a device selector to the SYCL runtime, it will look through all the devices you have available in your system, and it will essentially score them based on this heuristic, where GPU selector is one that would provide a positive score for a GPU and a negative for anything else, meaning that it only picks GPUs. You can define your own selectors that will do more complex logic, looking for particular features or even a very particular vendor. Or even in some cases, you could have selectors which will choose different selectors each time. Say if you want to do like a round robin selection, something like that. So it's quite flexible. One thing to note in SYCL 2020, this feature changed slightly. In that previously, device selectors had to be inherited from a specific class in order to be treated as a device selector. Now they're simply a function object, which means you could provide inline a lambda expression in there as well if you'd like. The second parameter to construct the queue is an async handler. So this function object is used to handle asynchronous exceptions thrown by the runtime. So after you enqueue your work and it's being handled by the SYCL runtime, if it encounters a problem, this is how the errors are reported back to you. So I will cover a little bit more about how this works, how asynchronous exceptions are thrown later in the talk. One main important thing to note here is that in SYCL 2020, the behavior is somewhat changed if you don't provide an async handler. Previously, if you didn't provide an async handler, errors wouldn't be handled. Now the default is that the program will terminate if there's no async handler provided. So if you forget to provide one, you'll definitely know because the program will terminate. Okay, so in SYCL, there's two main ways to manage memory. There's the buffers model, and then there's the USM model. Here, we're going to focus on the buffers model. So the buffers memory management model essentially creates the separation between the storage and the access of data, where buffers manage the data over a number of devices, and accessors allow you to access the data in one particular place. USM, in contrast, provides a more explicit memory management model, perhaps a bit closer to what you'd be familiar with if you've used CUDA. It's a little bit more explicit, doesn't provide the buffer model automatically handles data dependencies. The USM model doesn't. You have to be a bit more explicit about things. So essentially buffers manage the data across the host and one or more devices, and then the accessor represents a request to access the data on a particular device with a particular set of properties. And there's a few different ways you can use accessors to describe how you want to access it to give more information to the runtime, so it can make a more efficient scheduling choice. So here we create buffer objects for the input and output data. Buffers can be constructed with a pointer to the data on the host, and a range object, which is essentially a multi-dimensional index class, which describes the iteration space that the data will be represented in. Here, we're just passing a single value, so it's a one-dimensional space representing the size of each of these vectors. One note here in SYCL 2020, buffers now have CTAD, so they're no longer required to explicitly specify the template parameters. So the amount of code is now smaller. So one thing to note about buffers is that they manage data during their lifetime, which means that on destruction, the buffer will wait for any work that the queues are doing, which access the buffer's data to complete, and then they will synchronize the data back to the original host pointer if there's one available. So this means that once the buffer is destroyed or goes out of scope, you can be assured that the runtime is finished with your data and it's being copied back. So now to take a look at how you actually enqueue work to a device in SYCL. So all work is enqueued through command groups. So command groups are created by calling submit function. on the queue, which this takes a function which effectively acts like a factory for creating a piece of work that's going to be queued to the SYCL runtime. And this command group function takes a handler, and this is used to tie together the kernel function and the various dependencies, data dependencies for it. So inside the command group, we create an accessor for each of the buffers. So here we pass in the buffers and then the handler to link that together. And we also specify these tags, read-only or write-only, to define how we want to access them. One thing to note as well, these accessors are also used within the kernel function to access the data once you're running on the kernel. So yes, sorry, as I mentioned, the accessor is constructed from the respective buffer, the handler, and then the tag. And this tag describes how you want to access the data. So this is used by the SYCL runtime to manage data dependencies. So this uses this information to schedule kernels efficiently and know what one kernel may have to wait for before it can execute. And similar to buffers in SYCL 2020, accessors also have CTAD and these new tags, which make it a lot simpler to construct accessors than it was before. So next, inside the command group, we also define this parallel for invocation. So this defines the device function, which is essentially the entry point for the code that's going to run on the accelerator. So this creates the entry point for the code that could run on the GPU. One thing to note here is that SYCL 2020 kernel functions no longer require a template parameter to name them. So this was a requirement in SYCL 1.2.1. This is no longer required, so you don't need to specify that anymore. Although it is an option still available, you can still do it if you choose to, but it's not required. So the first parameter to the parallel for is a range object, and this describes the iteration space that the kernel will execute across. So essentially the number of iterations of that execution. Second parameter is a function object, which essentially describes the kernel function itself. And this function takes as a parameter an ID, which represents the currently executing work item. So out of all the iterations of that parallel execution, the ID refers to its own execution. So in this case, the kernel function is a lambda, and the body of the lambda is what's going to be executed on the accelerator. If using a lambda for your kernel function, the accessors and any other arguments must be captured by value, as these are copied over to the accelerator before it being executed. And now lastly, the actual body of the kernel itself. So in this case, because we're doing a vector add, we want to take each element of the two inputs, add them together, and assign it to the output. And for this, we use the subscript operator of the accessors, which were captured into the kernel. Okay, then finally, in order to wait for that work to complete, we call this wait and throw function, which will essentially wait for any work that's been queued to that queue to complete. It will also throw any asynchronous errors that were encountered. This is where the async handler comes in. So in SYCL, there's two types of errors. There are synchronous errors and asynchronous errors. Synchronous errors are essentially anything which is thrown outside of command groups or commands that are queued to a queue object. So, for example, creation of a queue, creation of a buffer, these throw immediately to the current thread. So you'd have to be caught by a surrounding try-catch block. Asynchronous exceptions are thrown from the SYCL runtime from anything that's running asynchronously. So whenever you enqueue work to a queue using a submit or another command, that will then get passed over to potentially some other thread being run by the SYCL runtime. So then any errors which are encountered will be stored and then rethrown once you ask it to be. And that's where the wait and throw comes in. This essentially tells the SYCL runtime you're ready to handle the errors. And at that point, they'll be then thrown and then caught by the try-catch. So it's really important to have a try-catch block around your SYCL code to make sure that you catch any exceptions that are thrown. And one other thing to note Just remember, upon leaving the scope containing the buffers, the data will be synchronized back with the original pointer. So in this case, when leaving the try-catch scope, the buffers would be destroyed, and then the output data would be copied back to the original vector. Okay, so next I'm going to cover the new sort of backend model in SYCL 2020, a little bit about how that works. So in SYCL 1.2.1, it was entirely based on OpenCL. So SYCL 1.2.1 was a high-level model for OpenCL. So there wasn't really a concept of a backend, because you had platforms and devices, and you could have multiple different platforms, and each platform would have different devices. Essentially, platforms representing the vendor or the drivers for various implementations, and then devices being the individual devices you could target. But now in SYCL 2020, this has been expanded to essentially a more generic programming model where you can target any number of backends, whichever backends the implementation support. So as an example here, we've got an implementation which supports an OpenCL backend, a CUDA backend, and also has this emulated backend. So this adds a new layer to the hierarchy where you have backends above the platforms, where each backend could have a number of platforms, which each in turn has a number of devices. So one thing to note here is that previously in SYCL 1.2.1, there was this idea of a host device. So this has changed somewhat in SYCL 2020. It's no longer called the host device, but this feature is still available through what's called the emulated devices. So a new feature of SYCL 2020 is you can query different devices for these aspects that essentially refer to different capabilities that devices can have. And this emulated aspect essentially describes a device which provides the same memory and execution model guarantees as a device, but it may not actually be running on hardware. It may be an emulation of the hardware, which generally means there's an expectation, which means that it won't be as fast, as performant as other devices would be. And it can also open up the opportunity for devices which can be debuggable as regular C++ applications. This is an option that implementations can provide. And then lastly, one other thing to note is that when you have an implementation, SYCL implementations with multiple backends, these backends can potentially represent the same devices underneath. So in this example, we have an OpenCL backend and a CUDA backend. Now, this is just representative. It's not of any particular implementation, but it's possible that an OpenCL backend could have the same NVIDIA GPU that a CUDA backend would, because they're essentially going through different APIs. So it's something to be aware of, to sort of be careful if you want to write code that would run across multiple backends. Generally, you use that in order to access different devices from different backends. But if you were to use the same device, you would have the two APIs conflicting, contesting the same resource. You'd have to be careful of that. Okay. So lastly, with this new backend model, this introduces a few different ways of looking at SYCL applications. So there's sort of generic SYCL, interoperable SYCL, and then vendor-specific SYCL. So first of all, generic SYCL is the idea of anything which is sort of core SYCL specification. And this is portable across any implementation. So if you write an application that is generic SYCL, that same code will run on every SYCL implementation, which means it's entirely portable. Then there's interoperable SYCL. So here, you can use SYCL's interoperability feature to interoperate with backend specific features. So for example, if you have an OpenCL backend or CUDA backend or Vulkan backend, for example, there's a possibility for these implementations to allow you to interoperate with these underlying native APIs. So kind of retrieving objects and constructing objects in both directions. So this is partially portable in that if you write, there's a standard API, which means that any implementations that have the same interoperability, the code would still be portable, but obviously it would only be portable between implementations which support the same backends and support the interoperability. And then finally, there would be vendor-specific SYCL. So this would be any code which is using either implementation or vendor-specific extensions, of which there are some provided. Different implementations have their own extensions, which are generally features which are proposed for upcoming versions of the SYCL standard that are being trialed out in consideration for a new version. So when you're using these features, generally other implementations won't have these features. So this essentially becomes non-portable in most cases. Although that doesn't necessarily need to be a problem, the SYCL API does provide macros that can test against different backends, and implementations generally have their own macros that you can use to guard against particular features and provide alternatives in order to maintain portability in the applications. Okay, and that's everything for me. I think at this point I'm going to pass over to Nevin, who's going to cover memory spaces.
You are still muted, Nevin.
Sorry about that. So the SYCL memory model was initially based on OpenCL, but we provide a higher level of abstraction. As Gordon just said, there's kind of like two models right now. There's buffers and accessors, which split up storage and access, and USM, Unified Shared Memory, which is more explicit than just regular C++ pointers. So there's kind of like, with buffers and accessors, there's kind of like 5 memory things. The main ones are like private, local, and global, and then there's also kind of related concepts, generic, and then an older one, constant memory. So private memory is just kind of like the smallest thing. It's private to a work item, and a work item is really just an instance of a kernel. And when we speak about kernels, it's really just a piece of code running on some little compute unit somewhere.
If I may, the slides have not yet been switched. Sorry.
Really?
Yes, we are still looking at Gordon's slides. There we go.
Okay. So private memory, yeah, is private to a work item. And a work item is just, it's a piece of work, runs on, GPU somewhere. And this memory, it's usually used for like, local stack variables or any memory the kernel needs. The next level up would be local memory. And so a bunch of work items together is a work group, but it's still a single compute unit, like a single GPU kind of thing, single piece of hardware. And local memory is accessible to all the items all the work items in the work group. So it's for things you need to share across work items. Maybe you're doing reduction and adding things together. You may want to put that in memory somewhere that they can all share. And then finally, there's global memory, which is accessible to like everything in the same context. And it's persistent across kernel invocations. But like if two things are writing to it, there's no implied synchronization. You'd have to do that yourself. And when we talk about generic memory, it's kind of like there's a virtual address space encompassing all this, local, private, and global memory. And there was an older one, constant memory, that's still available on OpenCL platforms. And it's the things that remain constant during execution. But it's not part of generic memory. And a thing called multipointer, I'll get a little bit into that later. The support for constant memory is now deprecated in SYCL 2020. And so here's kind of like the two ways to get it. You can use multipointer, which is a class that encompasses all this, address-space boundaries and interoperability. Or you can use raw pointers on some applications, but sometimes they're what we call decorated. There's a platform-dependent keyword to say what address space they're in, so that is not portable. But if you're moving more towards you just want your code is pointer-based, you may want to be using unified shared memory. And it's one virtual address space. It's a pointer-based model. And if you allocate a pointer on the host and you copy it to the device, it's got the same object representation underneath, but you may not be able to access it. It depends where this memory is allocated. And there's kind of 3 allocation types: device, host, and shared. So device allocations, this is memory that is attached to the device and the host cannot access it. If it needs it, you need to explicitly copy it via special memcopy like calls. The next is host memory. It resides on the host. And both the host and device can access it, although device access might be slow because it has to go over like a PCIe bus or something similar. It's good for things that like rarely access data and for large data sets that can't fit on the device. And then we also have shared allocations, which is implicitly accessible on both the host and device, and the data can migrate to where it's needed. And it could be implemented as a device allocation. And also you can, there's things like memadvise, and you can do to prefetch saying, okay, I know I need to use this on the device first, so make sure it's there. So when I need to use it, I don't have to wait. And memadvise is kind of a vendor dependent call, how it gets interpreted for doing this kind of thing. Support two different kind of allocation styles. There's kind of the traditional C, normal malloc call, lined alloc, etc., where you specify the size of the allocation. And also we support C++, a templated type that returns a pointer to the type, and also stateful like C++ 17 allocators. And really, the difference is, right, USM pointers are very close to regular C++ kind of things, and accessors, it builds the data dependency for you. It's not that one's better than the other, it's which fits your problem better and fits the code you already have better. Next, I'll move on to device copyable. So one of the things is we have to, we want to move data between kernels or just data between host and device. So how do we copy it? In C++, we would normally call the copy constructor. But in general, that involves running code. And there's a problem running code, right? Where would we run it? Does it run on the host, on the device? How does it magically, can it magically get access to both the source and destination bytes if it has to run code? So in general, all we can do is just memcopy the bytes between them. So for a long time, kind of use, trivially copyable is kind of a proxy for this. But for some obvious C++ types that should be trivially copyable aren't for historical reasons, like a pair of trivially copyable types or a tuple of trivially copyable types are not required and usually are not trivially copyable themselves. And trivially copyable has other requirements, like you have to have at least one copy move constructor or assignment operator, and the destructor and whatever you have of copy move constructor and assignment must be public and trivial. But the worst is layout and ABI are conflated and trivially copyable. This is why we can't fix pair, because it would be a breaking change. And a hugely breaking change if we try to make a pair of trivially copyable types trivially copyable in standard C++. So one of the things people have tried to get around this is a macro called SYCL device only, but that can violate the one definition rule. And for instance, if you look at the static assert, right, the static assert has only fires on the host, right? It's different, right? It violates one definition. And worse, if you want to pass this thing as a template parameter, is that value true or false? How does it instantiate? And this destructor, because I didn't say equals default, that makes it not truly copyable. But what does it mean to run the destructor just on the host but not the device, right? That means they're kind of doing two different, very separate things. Another thing, what if we just manually copy the bytes to device? Well, that also violates the C++ object model, the lifetime of objects. Just copying something over doesn't magically bring it into existence, and compilers take advantage of it. Normally take advantage of lifetime. That's one of the big optimizations they do. So it leads to undefined behavior, which means it may work today, but as compilers get smarter, it can easily break tomorrow. So what we added for SYCL 2020 is a new trait called isDeviceCopyable, which defaults to standard is trivially copyable, and we specialize it for C arrays, array, pair, optional, tuple, and variant of device copyable types. Remember before I said a pair of trivially copyable types should be trivially copyable? So a pair of device copyable types should be device copyable. We can't do this automatically easily unless we modify compilers because we don't have reflection. And users can specialize if they need to, at their own risk, of course. And we don't say whether or not we call a copy move constructor or assignment to do the work, because it shouldn't matter, it's just copying bytes. We also added AtomicRef in SYCL 2020. So way back in C++ 11, we had standard atomic was added to C++ 11, which is always sequentially, defaults to sequentially consistent because it's the safest one. It's the easiest to reason about. It owns the data and it always requires atomic access. But the worst part that we can't use it is because it cannot be moved or copied because atomic access requires hardware to know, at a specific address. So we cannot create objects on the host and copy them to the device. Just can't be done. So in SYCL 121, everything was in namespace CL : SYCL at that time. So CL SYCL Atomic was modeled in standard atomic, except it did not own the data and it defaulted to relax because it needed to be compatible with OpenCL. And that's been deprecated. So in C++ 11, there really was no notion of non-owning interfaces. We just kind of had raw pointers owned by convention. So if you had an interface with strings, you might pass a string, but that does an allocation. So you'd also pass a pointer and a size because it's non-owning and more efficient. And in C++ 17, Jeffrey Gaskell from Google brought a proposal for StringRef, which became StringView, which is a non-owning reference to string data, which is a pointer and a size. It's efficient. It's a great vocabulary type for interfaces. And it only cares about operations. So you can replace those two calls with a StringView call. So you can replace those other interfaces and have efficiency because standard string is implicitly convertible to StringView. C++ 20, we kind of went crazy with different non-owning types. We added standard span, which is non-owning reference to contiguous data. Ranges have lots of non-owning views in them. And the one we really care about here is standard atomic ref, which is a non-owning atomic access to data. And the user promises that they won't access the data in other ways, just through the atomic ref and only do atomic accesses. So again, we have our own version that we modeled on the C++ 21, but we have more template arguments. And SYCL is only required to support relax, but it might also support quite release and sequentially consistent. So here's kind of comparing standard atomic ref and SYCL atomic ref. Right, in C++ 20, T is triply copyable. In SYCL 2020, we say typically what types have to be supported. And typically, we don't support things like complex double yet. We might in the future, because it might require globally accessible lock table, and we just haven't figured out how to do that in terms of specifying it in SYCL. So it's more portable. As a memory order, we don't have a default for this because we couldn't really pick one easily. Like C++ pick is sequentially consistent, but that leaves out lots of devices we want SYCL to run on. Or we could have at least come down and relax, but then if C++ people are migrating your normal code, it may have a problem. Also, if you specify default order, it may change. As acquire, the default order might be default reorder might be acquire if default order was acquire release. Memory scope is just how memory ordering works. Again, no default, same reason. The safest one rules out lots of devices, and least common denominator leads to surprises. And then address space, which you've seen before. And so where is the object located? Is it generic? Is it global? Is it local? And you can override it, you're trying to do performance tuning. Finally, I'll briefly touch on things that are being added to C++ 23 that we're looking forward to. The first one is in the current working draft, multi-dimensional subscript operator, square brackets. So in C++ 20, we deprecated a common expression within square brackets. Like A of B comma C, that's deprecated. And weirdly, you almost never need that because other than macros can generate that because C is the index here. B is kind of evaluated but ignored. If you really need that functionality, you can parenthesize it inside there. And before we had square brackets, we kind of had three workarounds. The main one was use function call syntax instead of squares. Otherwise, or you can chain squares together, or you can pass a tuple-like thing inside. It's weird syntax. And the new one, the definition used to match the same operator of parens. And now you say A of B comma C, and that calls A operator of BC. And B and C are the two ordered indices. We're not currently making any changes to C arrays. In the future, C might want to adopt something like this. Well, that's the future. And the other thing we're looking forward to is MD span, which is a non-owning multidimensional array view. And the first to use operator square brackets. This is not in 23 yet. We have a C++ library evolution working group meeting on this next week. Hopefully it will be in 23. We think it can be. And so there's kind of three template parameters. We have extents, which describe each dimension, both for sizes known at compile time and runtime. Layout policy is data laid out for C or Fortran or a different way. And an accessor policy, this is kind of a default run right now. This is kind of so we can add like accessor functionality, kind of SYCL accessor functionality to it. And we're in the middle, right? We're actually just starting design of how do we want to use MD-span in SYCL. Like we want to support more than 3 dimensions, but how many? It's MD-span supports, it's variadic, as many as you want, but we can't efficiently do that, right? We want accessors, like maybe we want accessor like indexing to a USM pointer. We want to support strides, offsets, and subbuffers. Okay, and I'll now move on to Tom will take over and talk about reductions and group algorithms.
Yeah, thanks, Nevin. There we are. That's my screen sharing. So as Michael said at the beginning of the talk, another one of the big features that we added in SYCL 2020 are the reductions and group and subgroup interfaces. So to start with, I thought I'll show you an example. I'm going to revisit this example over the next few slides and show the improvements that we're making to the APIs in SYCL 2020 so that we're able to essentially reduce the amount of code on this slide. So in part, this does look like a lot of code, but it's sort of almost on purpose to show that sort of thing. And it's going to get more as we go forward and then simplified again. So this is in SYCL 1.2.1, the previous version of SYCL. And this is how we might want to implement a reduction. So for this, we might want to sum the integers from 1 to n, but rather than just using the closed form, we might have have an array of the data, which you can see at the top of the slide here. So I have an array of n integers, and I'm going to initialize them from 1 to n. And then this is the SYCL code underneath here, where I want to start doing the reduction itself. So for that, I have to create the reduction result as a buffer. And then I'm going to use the old, now deprecated atomic accessors that were in SYCL 1.2.1, so that I only have atomic access to the sum variable. So I'm guaranteeing I'm only going to do it atomically. I launch my parallel kernel and just add the data that I've accessed through my accessor to that final value. And then I can collect that single result, just one number on the host, and check that I got the right answer. So that's reductions in SYCL 1.2.1 using atomics. But for large numbers of parallel work items, we're going to create an awful lot of contention on that single value. If we've got a very parallel device, such as the GPU, where we've got thousands of parallel execution units all firing at the same time, for a simple kernel like this, they're all going to cause a great amount of contention on that atomic. So that's perhaps not the most performant way to implement this particular type of reduction. Nevin gave a really nice summary of the memory model just before, but it's worth just mentioning here how everything fits in with the space of reductions. In SYCL, we have this idea of work items and work groups. So that parallel for launches a kernel. That's the lambda function, essentially. And each of those instantiations of the lambda function are called work items. That's our independent unit of work that's executing that lambda. They all get run concurrently, and we can group those work items together into things called work groups. These is what you might have heard of as an ND range in OpenCL style programming, kernel programming as well. And we have a similar model in SYCL. So we have this 1, 2, or 3 dimensional work items grouped into 1, 2, or 3 dimensional grid of work that are grouped into work groups. There's a synchronization, so the execution model is important here, especially when we start thinking about writing performant reductions. Those work items can only synchronize with each other if they belong to the same work group. So we cannot have work items in different work groups. So on this slide here, these are 2 orange work items and they belong in the same work group. But this work item over here can't synchronize with any of the orange ones. Only the 2 in the work group can synchronize with each other. This is so that the implementation and the hardware is free to schedule the actual execution of the work groups either sequentially or in parallel or in any order it sees fit. So there's no way to synchronize and guarantee things will happen. So we can synchronize work items within the work group. And in SYCL 2020, we added an extra layer of this grouping. We can now group work items within a work group into subgroups. It's a one-dimensional only grouping, and it's sort of reminiscent of things like SIMD width or warps or wavefronts if you're into the GPU programming, where there's some stronger guarantees about forward progress and synchronization between those work items that belong to the same subgroup within the work group. With the memory model, as Nevin was saying, all work items have access to the same global memory. So this is useful when you need to have data shared between available to all the work items. But within a work group, we have this local memory. So we can use this hierarchy of execution and memory in order to write a better reduction, a more performant reduction, hopefully, in SYCL 121 using local memory instead of atomics. And so for this is how most people would have written reductions in SYCL 121. It's a massive slide full of code, and often it's very device specific. And lots of these things in here need tuning to the particular type of device that you'll be running on. This will generally work quite well on a GPU, but if you have a CPU, maybe this is not the reduction that you need to write. That's a problem when we're talking about SYCL. We want to provide people with portable code, and the backends that Gordon showed and the subsets there show how we can write portable code in SYCL. And hopefully we want it to be somewhat performance portable as well. We want one implementation that runs well across as many devices as possible with minimal specialization. So this sort of slide motivates the need for a reduction interface in SYCL 2020. I'm going to briefly just run down the slides before moving on so that you can see the kind of steps involved and how the improvements in SYCL 2020 solve some of these problems. First of all, we make a buffer of to hold our reduction result. Notice that this is no longer of size 1. I'm going to create a number of work groups and a number of work items in the work group. And I've chosen and hard-coded it in my program, 16 work items per work group. So I'm going to have n over 16 different work groups they're going to be launching, and each of them is going to produce a partial value. My reduction is going to have to be done in 2 stages, one result per work group, and then I'm going to have to accumulate it all at the end. Jumping to the bottom of the slide, you can see this. The host now no longer just receives one value back from the device. We have to call standard accumulate or some other mechanism to sum up all the values from all those work groups in order to compute the final result. Inside the kernel, in my command group scope, I use this local accessor to create 16 an array of size 16 integers, essentially, that's available in local memory for each work group to access. And then inside, I use that memory. It's called WG_sum. I use that to store the partial values of the array, and I have lots of barriers and a commutative tree style implementation to reduce all these numbers stored in local memory together to produce a single value per work group, which the first one can write back to my global memory so that I have the partial results. And of course, accumulating them at the end. So this is quite a lot of code. It's very prone to errors. There's lots of magic numbers in here. You know, I've had to choose 16. I'm doing clever things with making sure my memory accesses are all contiguous, those sorts of things. So this is why a reduction interface is very important in SYCL 2020. So the first of these, we can simplify this idea of implementing the within group reduction. And for that, SYCL 2020 adds group algorithms. Along with that came an updated interface for broadcasting data between work items in the work group and also an updated barrier. We also have these algorithms that are based on the C++17 algorithm library for collective operations between work items in the work group. So things like shifts and any of or all of for kind of testing data in the work group, things like scans and of course reductions. On the right, you can see the 2 reduction versions that we have for these group algorithms. And we often supply 2 versions of each of these algorithms. They essentially do the same thing. They're a collective operation. All the work items will collectively work together to perform this algorithm. And their interface differs mainly in how the data is presented to this interface. In the first one, this joint reduce, we hand over an iterator that shows the full extent of the data, and the work items will work together on that range of data from the first to the last to produce the result. The second version of the interface is where we supply one particular data item directly from each work item itself. So rather than providing all the data to work collectively on, this is a collective operation where the data is provided, perhaps calculated by each work item and provided directly to the interface. So we can use this to simplify that reduction from the previous slide. And for that, I'm now going to use the reduce over group. The rest of the slide has minor changes just to make it compatible with SYCL 2020, but the general approach is the same. I still create a value per work group, and accumulate it on the host, but use this the work group algorithm itself to do my reduction for me. So my kernel code is much simpler, but the general algorithmic approach is the same. This is much better because the implementation of SYCL itself can make good choices about what algorithm it should use based on the device. So finally, we can do a lot better, and it brings us on to the reduction API in SYCL 2020. This comes in the form, and it's inspired by a lot of work that was done with other C++ abstractions like Cocos and Raja that Michael talked about at the beginning. And really, we've taken portable ways that we've, through experience, been able to apply to lots of different devices and add them into the SYCL standard. Essentially, it's a two-part process. We create a reduction function to say this variable should have reduction semantics. And with that, what combination operation we should use and what identity it needs to have. And then we also pass the value to our parallel for, so that the parallel for itself knows it's a reduction, and we make the data available inside the kernel. There's some limitations on here which I'll let you explore in your own time. So for the example here, you can see that this is using the full reduction interface to SYCL 2020. I'm back again in the situation where I just create my scalar value that is going to be collected on the host directly. Inside the kernel, I can just use the reduction variable directly as it's passed in through the lambda. And I've got this reduction function here, which defines that this buffer here should have reduction semantics applied to it. And it should use the addition, the plus operator, in order to my reduction. This is obviously much more improved situation than before, where we had to hand write all the different algorithms that we could possibly need to implement our particular reduction. So with that, I'm going to hand back to Michael. Over to you.
Great, thank you very much. Really exciting to see how the close alignment is happening to C++. So I'll just close quickly with the future. I want to talk about how OneAPI and SYCL are working together to bring an open standard environment for developers. OneAPI basically provides developers with applied software. And SYCL sits at the heart of OneAPI, providing a mature open.
Looks like the presentation has stopped and we had some connectivity issues.
Okay, I just restarted. Thank you. Okay, so this is about where we sit with OneAPI, and that the DP C++ compiler is an implementation of the SYCL standard and makes targeting massively parallel hardware architecture simple and provides you with portability across different platforms. The SYCL standard is defined by the whole industry, with myself as a chair, and members from many major processor vendors, national labs, and research groups, ensuring that the standard continues to meet the needs of companies making processors and the software developers who want to easily target these processors. Now, we've been involved in defining the SYCL standard since the beginning, and we have spent many years implementing our own compiler, Compute CPP at CoPlay, which has been focused on delivering SYCL support to customers. We're also closely involved in working on the OneAPI initiative and have been implementing support for multiple processor architectures for DP C++ and some OneAPI libraries. Currently, We're adding support for all the features of SYCL on the Perlmutter pre-exascale supercomputer, and continue to extend this to bring to things like tensor cores. We're also working to extend support in DPC++ for the Frontier exascale supercomputer being built for Oak Ridge National Lab. And this work is in the development state, but we expect this to be ready for developers to use very soon. You can find instructions to set up DPC++ for CUDA support on this web URL, and AMD information will be coming soon. Now, the compilation step can't be simpler. Change the target flag to tell the compiler to make libraries for the NVIDIA CUDA target, as shown in the command line on this slide. Okay. So the strategy of the National Lab in the US is focused on enabling developers with a standard programming model, so the software they write can be deployed across multiple supercomputers that bring pre-exascale to exascale computing to researchers. Now, CodePlay has built a partnership with Lawrence Berkeley, Argonne National Lab, Oak Ridge National Lab, to enable SYCL on their next generation of supercomputers using DPC++, open source compiler project. And you can see a small snapshot of some of the frameworks and software that is enabled by using the SYCL open standard, from LAM, PS, a particle simulator, to Eigen, a linear algebra library used by the TensorFlow framework for tensor operations. So this slide basically is just saying how we plan to progress. You'll see it shows what is in SYCL 2020 on the bottom left. You're going to see some of the 40 features we have. And in the top box, you see our general larger philosophy that we have followed in our change from 1.1 to 2020 SYCL. And in the bottom right, you'll see what we have to do next in the form of conformance tests and working on conforming implementations, as well as new SYCL next features proposals. And on the far right, you see that our main goal is converging SYCL and ISO C++, while continuing to strongly support OpenCL, driving to support many different kinds of chips. Okay, so this is SYCL 2020. We have a lot of great features. We basically have increased expressiveness and simplicity for modern C++ heterogeneous programming. Look for us in future talks and tutorials we'll be holding at Supercomputing coming up, as well as CPP Summit, Pure CPP, just to name a few that I can think of. And of course, our major conference called CppCon in 2022. That's going to be held sometimes in April next year. Thank you to all the speakers. Thank you to everyone. Thank you to the CppCon host and our helper, Tim. And we're ready for any questions.
No questions so far. We're also at the end of the session, so possibly the Gather Town Q&A section or a session might be a better way to continue this discussion. We do have some time between talks, so if there are questions, I'm happy to read them.
Don't forget to use Discord to ask us any questions too. We'll have Discord open all week, so please use the track B to reach out to us.
Yeah,
and also after the fact too.
And I also want to mention we have a SYCL tutorial coming up next Monday, Tuesday, Wednesday, 3-day tutorial. So there's still time to sign up. If you want to deep dive into SYCL and much deeper than what we're doing here, please look into that as well.
We just received 2 questions. One from Ryan Kelly. I missed the definition of a group in the previous slides. It was a template argument taking about group algorithms. Not sure if there's any more question in there, but
yeah, I can say. As with some things in SYCL, it's not specified exactly what that type should be, and that was deliberate. In the group algorithms, we can say the group algorithm is going to apply to work groups or to subgroups. So essentially, that anything that conforms to those sort of 2 definitions in SYCL can be used to the group algorithms. So it's a flexible thing.
Thank you. The second question is by, I hope I pronounced this right, Arulsevan Madhavan. Other than the book, are there good learning materials?
So there are a lot of tutorials now running at various times and places. I've already mentioned the CppCon tutorial, and if you can't sign up for that, well, this is probably the best chance because it's going to be virtual. There's always going to be tutorial. We're aiming for ISC and CppCon and SC, depends on if we get accepted. And there are lots of them online as far as I can tell. So maybe some of the other speakers can say a little bit about some of the online access. And also have to mention SYCL.tech, which is everything about SYCL. It's like the ISOCpp.org website. It's the latest thing on it. So maybe other speakers can talk about some of these online access.
So I'd also mention SYCL Academy. So this is a cross-implementation sort of SYCL tutorial, has lectures and exercises. And this is the materials we'll be using for CppCon. So these are kind of recently been updated and are verified against CppCpp, DP, C++, and HipSYCL. So they're sort of designed to work across different implementations.
And this last slide I'm showing here is showing all the ways you can get into SYCL. All the GitHub, all the public GitHubs, places you can ask questions about SYCL. We monitor them to make sure that you can ask questions about the latest features as well as any issues you guys are having. 2 out of 3 of these methods don't need any money, like being the advisory on the advisory panel. The only one that needs money is if you want to be part of the working group and know the secret sauce of how we make SYCL. So have a look at this in the slide, and you'll be able to access many of the wide open source community forums. It truly is a product that is collaboratively built and is meant for everybody to build it for the kind of platforms that they specifically need, as opposed to any one particular one.
There are currently no more questions, so I guess thank you to all the speakers. And I would suggest the discussion continues in GatherTown.
Great, thank you.
Thank you all.